In this video, we're going to learn all about the concept of induction, which includes learning about Faradays and Lenz's laws. Before we can actually understand what induction is, we're going to talk about two experiments that we could perform. Focusing first on the diagram on the left. In this diagram, a person is moving a permanent magnet with a north and south pole toward a loop of wire, and that loop of wire is connected to an ammeter, or something that would measure current. We know from previous studies that a magnetic field can exert a magnetic force on a moving charged particle. Well, if you think about relative motion, all of those charged particles in the wire, specifically the electrons that are free to move about in a conductor, are moving relative to the magnet, since the magnet is moving relative to the wire. Therefore, this moving magnet would exert a magnetic force on the electrons in the wire, forcing them to move all in the same direction, creating a current. Now think about it. That magnetic force we know depends on the direction of the magnetic field, and it depends on the direction of the relative velocity of the electrons. First of all, that tells me that we care about the fact that the magnet is moving. If the magnet were to stop moving, that means that the electrons in the wire would not have a relative velocity in relation to the magnetic field produced by that magnet. So there would be no magnetic force, meaning they would not move, meaning that there would be no current in the wire. Again, if we were to also, instead of move the North Pole toward that loop, if we were to move the North Pole away from the loop, the direction of the relative velocity of the electrons would change, which means the direction of the magnetic force would change. So that tells me that the direction of the current would change. We're starting to see how a changing magnetic field could possibly produce a current, and that's the idea of induction. Let's now think about the experiment that would correspond to the diagram on the right here. This time we don't have a permanent magnetic field that is being moved closer to or further from a loop, but instead we have a separate circuit with a switch and a battery and a resistor and a loop itself. Now, we've learned previously that current can create a magnetic field. So if I were to close this switch, the current would travel out of the battery and it would travel around this loop and back through the resistor and through the battery. Current traveling in a loop causes a magnetic field. So in this situation, I'd go from having no magnetic field with the switch being open to having a magnetic field with the switch being closed. Guess what? If we have a changing magnetic field, that's going to exert a force on the electrons in the loop on the left-hand side, the one that's connected to the ammeter. So all of a sudden, we would have a current in that loop on the left-hand side, even though there is no battery. Both of these experiments help us understand the idea of induction. Basically, the current that's produced in the loop that is connected to the ammeter is called the induced current. The work that's done per unit charge to produce that current is called an induced EMF. Remember that EMF is kind of just another word for voltage. And the process of producing the current and EMF is what is called induction. So in other words, induction is that idea that a changing magnetic field can produce a current, even when no battery is present in your circuit. To figure out exactly how much current and how much EMF is produced, we'll have to understand something called magnetic flux. And we've already talked about flux before. Specifically, we talked about electric flux in the past. This is a similar concept, except we're dealing with magnetism instead of electrostatics. So magnetic flux, similar to electric flux, is used to determine the amount of magnetic field that passes through a loop. Remember when we talked about electric flux, we talked about the number of electric field lines passing through a certain area? this is similar. We're talking about the number of magnetic field lines, this time passing through a certain area. Here's our equation for magnetic flux. It has the same symbol as electric flux, except for with the B signifying that it's dealing with the magnetic field rather than an E for the electric field. And just like electric flux, we're going to take the integral of B dot dA. Remember that A, that area vector, is always perpendicular to the surface area of your loop, kind of whatever shape it is. Now, thinking about the units for this, we know that magnetic field is measured in Teslas. And we know that area is typically in meters squared. But a Tesla meter squared is not the unit we use for magnetic flux. Instead, we use the unit Weber, which is signified by a WB. Now, similar to electric flux, magnetic flux is important because of a very important law known as Faraday's Law of Induction. Faraday's Law of Induction tells us that the magnitude of the EMF that's induced in a loop made of conducting material is equal to the rate at which the magnetic flux through the loop changes with time. Okay, so magnitude of the EMF is equal to the rate at which the magnetic flux changes with time. Hopefully by now you realize that when you see that word rate, it means that we're going to use a derivative. And since it says how it changes with time, we're going to have a dt in the denominator. Here's our equation. The EMF, remember that EMF is represented by kind of a fancy E, equals negative d phi dt, where phi is the flux. Right now, we're not going to worry about that negative sign. We'll talk about that more as we get to Lenz's law. A little bit more about Faraday's law. If we have a coil that has n turns, that tells us that as long as those n turns are tightly wound, so remember like a solenoid, in other words, they're very close together, we can just multiply what we would get from one coil by the number of turns. So we add an n into that equation. So the one last thing I wanted to talk about with Faraday's law is how we could change the magnetic flux. There's actually 3 ways that we can do that. One of the ways to change the magnetic flux would be to change the magnetic field. Specifically, I'm talking about changing the magnitude of the magnetic field. A lot of times this would go with making it stronger or weaker, like we saw in that very first experiment where you were taking a permanent magnet and moving it closer to or further away from a loop. Another way to change the flux would be to change the area of the loop, making it bigger or smaller. And the third way to change the flux would be to change the angle between your magnetic field and your area vector. This is done commonly in motors and generators. So typically there's something that's spinning inside of them. A lot of time they'll have a permanent magnet inside that is spinning. And so as it's spinning, it's constantly changing that angle between the magnetic field that it creates and the area of the loop that's inside of there. So any of these 3 options would work for creating an induced EMF, because any of these 3 options would change the magnetic flux. Now, I mentioned we'd have to pay attention to that negative sign in Faraday's law. And to understand the negative sign in Faraday's law, we need to learn about something called Lenz's law. Lenz's law tells us that the direction of the induced current is such that the magnetic field due to that current opposes the change in magnetic flux. So the fact that it's opposing is where that negative sign comes from. I think that this law is best understood with a few examples. So let's say that we have a permanent magnet with its set north and south pole, and that permanent magnet is traveling toward this loop that's made of conducting material. We want to figure out whether that current induced would be clockwise or counterclockwise when viewed from above. So to figure that out, we're going to start off by thinking about the direction of the magnetic field that the loop is experiencing at the beginning of this movement. That means we have to think about which way the magnetic field of a permanent magnet is directed. The North Pole is nearest to the loop, and we know that magnetic fields point away from north and toward the south. So it kind of would go like that, right? So everywhere near this loop, the magnetic field is going in the downward direction. So again, task number 1, determine the direction of the magnetic field. And we're going to call it external magnetic field. Okay. How is that magnetic field changing? Specifically, how is that external magnetic field changing? In this case, the external magnetic field is getting stronger because the magnet is getting closer to the loop. So we have a downward magnetic field that is getting stronger. Lenz's law says that we want to oppose the change in magnetic flux. Well, because it's a downward field that's getting stronger, that tells me that the magnetic flux is increasing. And so we want to oppose that. We want to decrease the magnetic flux, right? So opposing that means we need to determine the direction of the induced magnetic field. And again, that induced magnetic field would oppose that. So that means that the induced magnetic field would be upward because it's opposing the strengthening downward field. And finally, we have to figure out the direction of current. And for that, we go back to the right-hand rules that we learned in chapter 29. If the magnetic field is pointed upward, then my current must be traveling counterclockwise when viewed from above. So counterclockwise is the correct direction in this case. Let's do a little thought experiment to help us make sure if we really understand this. Let's say instead of the North Pole moving toward the loop, let's say we're moving away from the loop. I'd still have a downward field, but this time the field would be getting weaker, which means my flux would be decreasing, and we don't want the flux to decrease. We want it to stay the same because it opposes change. That means that the loop will have an induced magnetic field that's in the same direction as the external magnetic field, so the induced field would be downward. Using the right-hand rule, that tells me that when viewed from above, the current would be clockwise this time. We'll do some practice with Lenz's law, and definitely some problems using Faraday's law when we meet next.